Hello, and welcome to Acoustics Derivations. In this video, we will be deriving the conservation of momentum as we work our way towards deriving the wave equation for waves in a fluid. To do so, we will consider a control volume fixed in space with some arbitrary volume V and some arbitrary surface S. And we know that the outward normal is n vector, and we can also consider a differential element ds. We note that the fluid inside the control volume has density rho. Now, at least for me, I find it really helpful when deriving the conservation of momentum and mass, but we're talking about momentum here, to write out the conservation of momentum in terms of actually in words before going to the math. Well, the conservation of momentum is what I've written here, the rate of increase of momentum in V, which is equal to the net momentum inflow, and that's important, through S, plus the forces acting on the control volume. So let's start with the rate of increase of momentum in V and work our way through it. So what is momentum? Well, if you think back to your freshman physics days, it's a mass times a velocity. And we'll represent that here as the volume integral of rho times u dv. Okay? So it's if you look at units, that has the same units as a mass times a velocity, because rho, the integral of rho, the volume integral of rho is, of course, mass, and then we have particle velocity as well, which is u here. Well, if we want to look at the rate of increase of momentum, well, that's simply just the time derivative of the integral. But we know that the control volume is fixed in space, thus the volume of the control volume does not depend on time, so we can actually move the time derivative inside the integral. Thus, we see that we have calculated the rate of increase of momentum in V as the volume integral of the time derivative of density times particle velocity. Okay, so now we want to think about momentum flow. Well, you could either consider a momentum flow as the as a mass times an acceleration, or what we will consider here as a mass flow times a particle velocity, or at times a velocity. So we can represent that as m dot u, where the dot refers to a time derivative. Well, we ask ourselves, what is mass here? Well, it's either rho times rho times volume, or rho times the surface area times the length, and that's how we will write it here as rho s dot u. So if you consider u as just a length, not as a length over time, that gives us a mass, but the over time gives us a mass flow. But then we need momentum flow, so we multiply once again by another u. Well, we can represent S as n dot S which can be rearranged as okay, which can further be rearranged as rho u dot n s. Okay, so you can see that by noting that rho is a constant, so it isn't part of the dot product there. So we've made this we've described the momentum flow such as this, but we want momentum inflow. And it turns out to accomplish that, we need to put a minus sign in front of it. Um, if you look at the u dot n in the considering n being the outward normal and the flow going in or going out, you can see that we do indeed need a minus sign for this to be true. But we want it in terms of this expression in terms of an integral because we don't have a constant s. So we note that this is really negative times the surface integral of rho u dot n ds. Okay, so now we have the momentum inflow. But if we look up here, we know that we still need one more thing, the forces acting on the control volume. So we have the rate of increase of momentum in V, and we have the net momentum inflow through S, but we need the forces acting on the control volume. The forces are, we can break them up into two components, which we'll call a body force and a surface force. The body forces can be written as the volume integral of rho times b dv, where b is some body force per unit mass. And you can see that if we take the integral, then the integral of rho dv is of course a mass. So this is a force. We can the most common, so body forces aren't very common in linear acoustics, but the one you might run into once in a while is gravity, and that shows up if you're looking at like propagation into the atmosphere where you're not on a relatively constant plane. So even though that's not very common, we're going to include it here just for generality. Now, when it comes to surface forces, if we consider the control volume surrounded by more fluid, we know that the surface force on the control volume has to be the pressure due to the surrounding fluid. As such, we will consider the surface force, and I should mention here, I should have mentioned this earlier, we're actually neglecting viscosity, which would, if we included viscosity, that would be would factor into another surface force, but that makes things significantly more complicated, and so we're going to ignore that. So the only surface force we will be considering is the pressure due to the surrounding fluid, which can be represented as the surface integral of pressure P times N ds. So now, great, we have our forces acting on the body. So we can add these components together or combine them together in the form of the equation. And I'm going to do that, and I'm going to move everything to the left-hand side and equal it to 0. So we have the volume integral of the time derivative of rho u dt plus the surface integral of rho u dot n ds plus the surface integral of p n ds minus the volume integral of rho b dv, and that's equal to 0. So let me clean up that b just a little bit. So this is the integral form. Let me write this down. This is the integral form of conservation of momentum equation. So that's a perfectly valid equation, and it has use in some applications. However, we want to derive the wave equation, and to do that, we need the conservation of momentum equation in terms of in a derivative form rather than an integral form. To do that, we will invoke the divergence theorem. Whoops. twice on both of the surface integrals. So first, we will be able to write this as the volume integral of the divergence of rho u dv. And we will also be able to write the surface force, or the surface integral of P and ds as the volume integral of the gradient of P dv. Now, note that this is a corollary actually to the divergence theorem. Okay, so now we can put these all together again. So we have the volume of the volume integral. Oh, and we note that now everything's in terms of the same volume integral, so we can combine it into one integrand. As I'm doing here. Okay. Well, now we once again note that the volume of the control volume is arbitrary. In other words, the only way for this integral to be true is if the integrand itself is equal to 0. So we obtain the following. Okay, so this is technically the derivative form of the conservation of mass, conservation of momentum equation. However, we can simplify it even further if we recall the conservation of mass equation. So the conservation of mass in derivative form is d rho dt plus the divergence of rho u is equal to 0. So let's expand the first two terms of our solution here. So we have that d rho u dt plus the divergence of rho u u. And if we expand that out by a chain rule, we get u d rho dt plus rho du dt plus divergence of rho u times u plus rho u dot. Okay, so we have that. Now, if you look at the conservation of mass equation, you can see that this term and this term are simply the conservation of mass with a u. Sorry, I dropped the vectors there. The u out in front. So these actually cancel. Thus, we obtain the solution, or the derivative form, I should say, of the conservation of mass equation as follows. And if you're one to box things, this gets a box. This is the derivative form of conservation of momentum. Now, you could also write this in terms of, I believe it's called a total derivative. given by d dt, which is equal to lowercase, so capital D dt is equal to the partial of the derivative with respect to the partial derivative with respect to t plus u dot the gradient, which then you could write the derivative form of the conservation of momentum in as such. Now, I personally don't like doing that because, at least from what I've seen, if I ever want to use the conservation of momentum equation, I need to you need to take it out of this form and put it back into the original form. So at least for everything that I've done, now I'm sure there's plenty of applications to use it to use this form instead with the total derivative rather than the partials like I have up here. But you just have to, for me personally, I just always find that I have to convert back to the original thing. So, but it's important to know that you could write it like that. You might see it like that in some textbooks. Now, one final thing before this video is over. I'm not going to do it here, but I want to note that the conservation of momentum equation can actually also be derived from the Reynolds transport theorem if you make a specific substitution, namely, let u be the intrinsic variable and m times u be the extrinsic variable. If you do that and then do all the math, you will find, or you will obtain the same result. So that concludes this video. Thank you.